doing essentially two different experiments trying to identify an amino acid. The amino acids that we have for unknowns are lysine, serine, glycine, glutamic acid, phenylalanine, and leucine. So those are the 6 individual amino acids that you'll have for standards, and you'll have an unknown that's a mixture of all 3. And you're trying to figure out which 3 are in that mixture. And we're going to be using 2 major techniques. One is TLC, which stands for thin layer chromatography, and one is ion exchange chromatography. Now we'll talk a little bit more about ion exchange chromatography probably in a week or so when we apply it to proteins, but it applies to amino acids with the same principles, and it really is key, especially the analysis, to what we just hit in lecture about PIs, places pH where things have charge and places where they have no charge. So that's why I put this slide really first, even though we haven't had a whole lot of background, is because it starts you thinking about PIs, and essentially to make this guy work and understand it, you'll have to calculate for yourself the PIs of all 6 of those different ones. And from that, you'll be able to rationalize why things come out the way they do. Okay, so let's start with TLC. Now TLC is a technique that how many people are in or have been in organic lab? 1, 2, 3, 1 from every group at least. So you're all familiar with this. So somebody can tell me about TLC. Somebody want to just get up and start talking? Okay. Well, let's just start with the basics. What you're going to be using is is media right there. And I put it under this glass just so you don't go up and accidentally touch it. And first things first, when you pick this guy up and use it, any special technique I have to use?
Don't touch the gel.
Don't touch the gel. So you have to pick it up carefully from the edges, like that. Don't touch the gel. Now, I hand cut these, so some of them might be ragged at one end, or some of them might be ragged on one side. When you use this, if you've got a ragged end, put it up so there's no solvent and it doesn't touch any of your material. Okay, so this is what it looks like. The people who haven't done this before. Back is aluminum, and it has it's not anything that we're working with, it's just a backing to make it solid. And the front is silica gel. Now the silica gel is, silica is Si, and what a silica gel is, it's Si linked to oxygen, linked to another Si, linked to another oxygen, in a complex 3-dimensional net. But the main part of it is, one side of the silica has an OH on it. So that makes this white material very polar. Now what you're going to be developing it with is a solvent called, the book calls it PAW, and I think they actually tell you what the PAW stands for. It stands for propanol, acetic acid, and water. So it's 4 parts propanol, 1 part acetic acid, 1 part water. And okay, you guys told me that Dr. D doesn't go much into nomenclature, so you may not know what propanol is. But methyl ethyl propyl, it's a 3-carbon unit with an alcohol at one end. So these 2 carbons here and that one there make it nonpolar. It's got a little bit of polarity from that OH there, but it's primarily nonpolar. So the separation you're going to get here is a separation by polarity. Things that are polar are going to want to stick to the silica gel, so they don't want to move. Things that are nonpolar are going to want to move with the solvent, and the more nonpolar they are, the more they're going to move to the top of the gel. Very simple as that. So you're doing a separation based on polarity. Now if you look at this, we've got a couple of nonpolars, phenylalanine, leucine. We've got a couple of kind of intermediate polarities, serine and glycine, and then the glue and the lyse are charged, they're different. So you're going to see a mix, and many times you'll have a couple of these guys coming out at the same time because they have very similar polarities. Added to the fact that I don't know how big the gels were you used in organic, but I'm giving you these little guys, so you won't have a whole lot of distance, see a whole lot of separation. So the chances are you're not going to be able to just look at this and tell which 3 amino acids you have. Because of that, that's why we go to a second technique that separates based on an entirely different principle, and that'll help us between the 2 principles. You should be able to uniquely identify your amino acid. Okay, so we covered the background. Setup. Now on this, okay, you guys know this already. Pick it up by the sides. Then what? How are you going to locate where your amino acids go?
Draw a line on the bottom and then you put your...
Draw a line really light with the line. You don't want to damage the silicone gel with your pen or with your pencil. Don't use a pen. And make it a little bit above the bottom. And since you don't have room on this little guy to have all 6 amino acids and your unknown, what I want you to do is have 3 amino acids in your unknown. And then the 2 groups here, between your 2 groups, cover all 6 amino acids. So you do 1, 3, you'll do another 3. You guys, similarly, each side of the bench, one group does 3, the other group does the other 3, so you have to coordinate, and you put your own unique amino acid on there, and then you can compare. And between the 2 groups, you'll have it all. You'll have it all. Isn't that great? Other things to remember. Don't put your line down there too small. You want, when you put this in your developing tray, you want the solvent to be below where the dots, where your amino acids are. Why is that?
So it can travel up and separate them?
So it can travel up and separate them. If the solvent is above your amino acids, they'll just dissolve into the solvent and nothing will happen. So make sure that when you put it in, you've got the liquid level below where your amino acids are. Now I don't have any fancy, there are fancy little chromatography setups. We don't have any of that. So what we're going to do is we're going to do a quick fudge, and that's what this is trying to show you. The quick fudge is I put out a 100 ml beaker in a watch glass. So this piece should just fit in. So you'll have your solvent in there first. The PAW solvent is right here. PAW solvent or PA on that side. That should just fit in the bottom of the 100 ml beaker and sit upright. And that one is just a little high. And then put the watch glass over the top. Now that's not a terribly great seal. So then the second thing I want you to do is to put a 1,000 ml beaker. You should have a 1,000 ml beaker in your biochem drawer. So just grab one out, give me a quick demo. 600 may work. Yeah, 600 works. Put that over the top to give a little additional solvent so we don't have to be sniffing that PAW solvent all day long. So that's the setup you have. And as the book says, once you get this guy set up and going, this will take half hour to an hour to develop. So you just ignore it and you go on to part 2. Now the final thing, we'll assume that it all finished. What's this thing about an RF value? Anybody remember what an RF value is? Retention factor. And all that is a quick measurement of how far this guy moved up. Second thing is, how are you going to tell when you've got an amino acid? If you look at these solutions that we have, they are all clear and colorless. And the amino acids don't have color. How do you know where your amino acids are?
With the black light.
With the black light. The gel itself is impregnated with a fluorescent material. And essentially, whenever you have anything covering that fluorescent material, it gives you a different color. So you'll go up and use the black light and just look at it. Now when you look at it, the first thing you do, as it's developed, when it's completely developed, you'll have your line with the thing, different spots there. And as you first pull it out, make sure at this point you write on it with your pencil again where that solvent actually got up to. And then the retention factor is if this is one of your pure amino acids, you should have a spot there. This is another pure amino acid, you should have a spot there. The retention factor is simply measure this distance, measure the total distance, and what fraction of this total distance this guy gained. Why do we have to use retention factors in this lab? What's the advantage of using retention factors? You have to do a calculation, but why are we going to use a calculation? Why can't we just measure the distance from the bottom to the top?
So that it's standardized and it can be repeated.
So it's standardized and can be repeated, and especially since you guys, each bench, is doing a set of amino acids. This set of 3 people here might only let it develop and bring it up 5 centimeters. That group over there might have let it develop up to 6 centimeters. And so with you 2 guys trying to compare data and trying to come up with the same set of unknowns, if you travel 2 different distances because you had 2 different groups of data, you can't compare them. But when you use the RF factor makes it independent of how far you actually move, because it's just what fraction of movement you got. So that will make it so you can compare everything. And then you'll have your unknown that'll probably have all sorts of interesting stuff going on. Okay, I think we've covered that guy. Now, ion exchange chromatography. Now, this is one you didn't do in organic. We'll talk about it more later, as I said. But first thing we say is it's a resin. So that column in front of you is your ion exchange column. And if you look really, really close, you can see that there are tiny little beads in there. And essentially, they're tiny little plastic beads. And built into the plastic of the bead are SO3 groups. So each little bead is covered with a bunch of SO3 groups which have a negative charge. Now, with the bead being your solitary phase, the stationary phase that doesn't move, it's going to be attracted to things that have positive charge. Hence the name, we call this a cation exchanger, because what will happen right now, it's got sodiums that are just ionically bonded to the SO3 groups. And as you put your amino acid on, if your amino acid has a charge, it'll swap out amino acid with a positive charge, sodium come out, your amino acid will be bound. And then as we change the pH, at some point, you're going to change the pH enough that your amino acid no longer has a charge, and when it no longer has a charge, then it comes out. Okay, the write-up on this is actually pretty good, and the big issue, the big thing you really have to pay attention to is this statement that they make in the book. If the pH is less than the pi, it will be positive. And this is a general rule. Don't just think about it for this lab. Think about it in life. Whenever the pH is less than the pi, whatever you're dealing with will have a positive charge. That's an amino acid, that's a protein, that's DNA, it's anything. So when the pH is less than pi, you'll have a positive charge. When pH is equal to pi, we just talked about that yesterday, what happens?
It's neutral. It's neutral.
Neutral. And if it has neutral, and this guy is binding things that are only positive, that guy will start to come off. And if the pH is greater than the pi, then you have a negative charge, and that will definitely come off because it's not even attracted to the column at all. So what you're putting on is a mixture of these three different amino acids up there, and depending upon their pi, what you start off with is you're washing it with a pH 3 buffer. And in the pH 3 buffer, the things with the lowest pi may have their pH, the pH even at 3.3, even at 3, might be greater than the PI. So if you've got a really negatively charged amino acid, it might be coming straight through because it's not bound. And so that's what should come off first. Then you change the buffer to pH 6. As you boost it to pH 6, anything that has a PI between 3 and 6 should come off. And then you hit it with the third buffer, pH 11 buffer, and at that point, anything with a PI between 6 and 11 comes off. So that's how we're separating things. We're separating them basically based on their PI. So we've got one separation based on PI, we've got another separation based on polarity. Now in this one, technique is a little bit different. First thing you can do when you start your column is simply take off the bottom and let it drip. If it doesn't start dripping right away, oh, this one is very nice, it dripped right away. Give it a little tap like that, and it should start dripping. When the liquid is right down, the water is just right at the top, you can't even see meniscus. Then you close it up and you put on your mixture of amino acids, your unknown. And I think it says the change in the procedure is 0.25 mils instead of 0.5 with the new procedure. Because what I'm trying to do is make this faster. This is the one that takes a long time, and in years past it's taken a good long time, and I'm trying to make it faster. So the first thing you do, get it on there, get that guy on there, and then you start, you don't have to measure exactly how much, you just grab pH 3 buffer, put it on there, and you start collecting fractions. And the way you're going to collect fractions, rather than into a test tube, there's a couple of bags of Eppendorf tubes. Just drip them into the Eppendorf tube, and on the Eppendorf tubes, you should be able to, you can see, what do I say, 1.5 mil fractions? Right there at the top is a 1.5 mil line, so just fill it almost to the top. And I think I say 10 of these.
I think it's 15.
15.